Hello, multivariable calculus students. This is Mr. Johnson, and we're going to start section 10.3, which is on arc length and curvature. And this is by far the largest section in chapter 10. So there'll be a number of different videos within this particular section. We're going to look at arc length in this video. And you can see the equation for arc length written in the notes. And this is from the last year's math, BC calculus, or the IB equivalent. And so I want to make you aware or just remind you of the rectangular form for arc length. And this is when we had equations that had, let's say it was y as a function of x or x as a function of y versus a parametric form, which had a t in it. So the general form that we have that we will be utilizing here in multivariable calculus as well has a t in it because it's in that parametric form. But if you don't have that parametric value and you have just x's and y's, you may see arc length as the integral from a to b of the square root of 1 plus the quantity dy dx squared. And we did this last year, so if this looks familiar, that's why. And that's in terms of x. And then the other one would be the integral from a to b of the square root of 1 plus the quantity dx dy squared, and that's in terms of y. So again, we have these two different rectangular forms for the arc length, but again, we're going to utilize the main one that we used last year, which is in terms of t. So you can see that the equation for arc length is really similar. We just add the third component, so the component for z, so we have dz dt, and you can see the formula down here. So we're starting with this vector function r of t, and we're assuming that that we have a situation where the derivatives of each of the components is continuous. And so if we traverse the curve exactly once as t goes from a to b, the arc length is given by this formula, which I know looks really ugly, but keep in mind that more simply it is the magnitude of r prime. So again, the square root of all of these components squared is the same thing as the magnitude of r prime. Remember, in our textbook they use the single bar, and in our class we often are using the double bar. So it's the magnitude of r prime of t dt. That's going to be our arc length. You can see in the diagram over here, it kind of goes through the mindset behind arc length as a calculation. So it says that the length of the space curve is the limit of the lengths of the inscribed polynomials, or excuse me, polygons. And so you can see that what you're doing is sort of taking this smooth curve and you're making these little sections on it. And as you make those infinitely small and we total those all up with our integral, we're going to get the length of that arc, or the distance that's been traveled along that curve. So let's go ahead and try one. We have example one, which is the length of the curve r of t when t goes from 0 to 1. So our very first step here is to find the derivative of r, which is 2 and then 2t and t squared. And so that's r prime. We're going to do the magnitude of that. So the magnitude is going to be the square root of 2 squared, so 4 plus 4t squared plus t to the fourth power. And this particular case, we need to be able to work with this one. So I'm actually going to factor this. We get t squared plus 2, and we square that. So that's going to be the factored form for 4 plus 4, t squared plus t to the fourth. And then if we take the square root of that, we of course get t squared plus 2. So the magnitude of r prime is going to be t squared plus 2. And then our job is to integrate this from, so the length here is from 0 to 1 of the magnitude of r prime, which we just found is t squared plus 2. And then we have the antiderivative, so 1/3 t cubed plus 2t. We go from 0 to 1, so we get 1/3 plus 2, which is 7/3, and that is the length of the curve when t goes from 0 to 1. Okay, let's go on to the next page and try another one of these examples. All right, for example 2, we're going to take a look at the length of the arc of the circular helix with vector equation r of t. and we're going to go from the point 1, 0, 0 to the point 1, 0, 2 pi. Now in this problem, we're not given specific t values, and so we do need to find these given the points. Remember that we have in our function x of t, y of t, and then z of t, and so each of these points is a component of x, y, and z. And usually what you can do is find one that is easier than the others. So for example, if you have x is equal to cosine of t, and we know that's going to be 1, well then we could solve for t that makes x equal to 1. We could take sine of t, which is equal to 0, and we can figure out a t value that makes that 0, and so on and so forth. However, in this problem, as you can see, this third component is simply just t, and so the values of our points that we look at, just the third component, the z component, that is defined as t, therefore t goes from 0 to 2 pi. So again, that's one of the ways that we can save ourselves a little bit of time, is to look for the easiest component to calculate whatever the t value is. All right, let's go ahead and calculate r prime of t first. So r prime of t will be negative sine t, and then cosine t, and then 1. And we're going to find the magnitude of this. This is one that you'll probably want to memorize because we use a helix a lot. I've talked about that in the in section 10.2. Helix vector function is pretty common, and so when we find the magnitude of this, I'm going to write it out the long way, but often what we can do now is just simply simplify this down, and we'll know what the answer is, I think, in the future. So we have cosine squared plus sine squared, which is 1 plus 1, and so the magnitude of the helix is the square root of 2. So in other words, the magnitude along the helix curve is constant. It doesn't change as t changes. And that's kind of a unique characteristic of the helix curve, because most curves, you're going to have a magnitude that changes by a variable, so the magnitude will have a t in it. In this particular case, the magnitude of the helix is actually just constant no matter what t is. Okay, now what we have is our integral for the length, which is from 0 to 2 pi, and the magnitude of the derivative function r prime is square root 2, and then we have dt. So the antiderivative, now again, when you have a constant, if you think back to when we did integrals, we could do the antiderivative and get square root of 2 times t, and then go from 0 to 2 pi, and we would get 2 pi root 2 minus 0. But really, again, you want to think about how to save yourself a little bit of time. If there's a constant here, the integral is simply the constant times the difference of the limits. So in other words, you could say that the answer would be the square root of 2 times the difference of those limits, which again is the same thing. And we'll look into that as we get into more difficult integrals, like for instance double integrals and triple integrals. But either way, the length of this particular curve is 2 pi square root 2. Okay, let's talk for a moment here about changing your parameter. Now, there's all sorts of ways to change our parameters. We could change the parameter of t into something completely different. This little example that we have shows what's called the twisted cubic, which is t squared, t cubed. And in this particular one, we're going to go from 1 to 2. You could change the parameter and say that we want to let t equal e to the u, and then all of a sudden the exact same identical curve would be represented by a completely different looking vector function, e to the u, e to the 2u, e to the 3u, and the parameters obviously change as well so that it maps the exact same curve. But if you were to graph these two, you would get exactly the same portion of the twisted cubic. And the reason we can do that is because with vector functions, it's all about how to access the point. And you can access the point in a variety of methods. When you come up with your vector, your numeric vector, if I plug in 1, I get the vector 1, 1, 1. And when I plug in the value of 0 for u, I get the vector 1, 1, and 1. And so there are many ways to change the way that the vector function looks and yet get the same result in terms of where the space curve is. So if we were to use the same kind of idea and look at just the simple length of the arc, again, the length of the arc should be the same. It's exactly the same portion of the curve, it just looks different. We could, for the first one, take the integral from from 1 to 2 of the derivative, of the magnitude of the derivative. So that's going to be, let's see, the derivative of t is 1, so we have 1 squared. Derivative of t squared is 2t squared. And the derivative of t to the third is 3t squared. And again, we're doing the magnitude here. And if we were to do the second one with e to the u as a substitute for t, we have the integral from 0 to the natural log of 2, and we take the square root of the derivative of that one, which is going to be e to the u, and we're squaring it, plus that's going to be 2e to the 2u, and we're going to square it, and then we have 3e to the 3u, and then we'll square that as well, du. So the question here is, are these two the same if in fact we're able to trace out and map out the exact same curve along the twisted cubic? So I just paused for a second to type these both into my calculator, and we do in fact get exactly the same value, which is what is expected here. And in this case, you're not doing either of these by hand. There's really not a good way to find the antiderivative. But the point of the matter is that we can take a look at some sort of curve in space, and we can look at just a section of that curve, and we can represent it with multiple vector representations. Okay, I just wanted to pause for a second to write out this statement. So again, the idea here is that we have two different equations, two different vector functions that are parametric representations of this exact same curve. And there are many more, by the way, that could also fit into this category. So when we're calculating the arc length, or the distance between two different t values, the answer is independent of that parameter that we used. The key, however, is that when we pick the parameter, when we're looking at representing it in such a way, we want to make sure we don't pick a function or pick a expression that limits the input. So if you were to put something in there like the square root of t, and all of a sudden you limited the fact that t could never be negative because the square root of t would have an error, that's going to be an issue. But we went from t to e to the t or e to the u, and there aren't additional restrictions that would be in place there. Okay, let's go on to the next page. All right, so on this page, we're going to look at a couple things that actually will lead into the next video, but the length of the arc is given there for us just as a quick review, and we're going to talk about the idea of taking a vector function that is in terms of t. So in other words, the vector function is defined as an input of t. Maybe that's time if it's a particle in motion, but based on t, we could say that I'm going to go from t is 1 to t is 2, and I can figure out the length covered or the distance covered along that particular section of the space curve. So what we're going to do now is we're going to take a look at the vector function, and instead of having an input value of t, we're going to have an input value of the actual arc length. So what that means is that if you had a function that was defined by arc length and you know where we started, we could say, well, I'm going to decide that I'm going to travel 7 units along the curve, and then we're going to be able to get the position at the time where that 7 units is then completed. And so it's a different view of the vector function itself. Now, the first part I'm going to do here is actually connected to a formula that I have a little bit later, so I think I'll probably rearrange this next time around. But remember, we have our arc length, which is s of t, and it's the integral from a to t of some magnitude of the derivative of r, and they're using u as a dummy variable here. The limit is t, and so they cannot use a t inside of that as well, so they're just having those variables changed just so that it's better format in terms of how it's written. If we were to take the derivative of both sides, so I'm going to take the derivative of s with respect to t, so I'm going to get ds dt. And remember, by the fundamental theorem of calculus, if I take the derivative of this integral with a numeric lower limit and a variable upper limit, I simply get the magnitude of r prime of t. And again, that's based on the second part of the fundamental theorem you learned last year. It's the derivative of an integral with a variable upper limit. So you could maybe make a note that that's by the FTC. Now we're going to use this in a formula here in the next video. So kind of lock it away for a moment, but we're going to use this relationship of the derivative of the arc length with respect to t. Okay, in example 4, we're going to try to change the parameter. Now again, look at the original. The original has a parameter of t, so the input is t for each of the components. And I'm going to change this so that it's that the input of this particular vector function is going to be arc length rather than time. So the input's going to change. We are going to start from 1, 0, 0. Let's go ahead and define what t is. Now remember, in your vector function, you have cosine t, sine t, t. This is basically the exact same one we just used. That t is going to be the easiest one to figure out. So we're looking at t starting at 0 in this particular case. Now I'm going to walk you through, first off, here's the idea. We're going to go from r of t, and we're going to change this to r of s. So we're having the input change. Now the easier way to think about this, I think, is that the input will be t equal to some variables of s. So in other words, it's going to be r of t of s. We're going to change the input to be arc length. Okay, I'm going to set this up for you in sort of a stepwise process so it makes a little bit more sense, because this can be quite lengthy in the process, and you'll see a couple that are a little bit faster, but a couple of these are kind of algebraically intense. So the first step is that we're going to find the magnitude of r prime of t. And so in this problem we have the helix that we've talked about so much. We already know, just because of the other examples, that the magnitude of r prime of t is going to be the square root of 2. So we don't have to show all of that work. We're going to start to have that memorized just because of how often we're going to use that. Okay, the second step then is going to be to find s of t. Now remember, just above on the same page, we have s of t, which is equal to the integral from a to t. Now remember, a is the starting value, and in our case, we already defined that as t is 0. So we're going to go from 0 to t of the magnitude, which is the square root of 2. And then remember, we're using u as just a dummy variable, so du. So this gives us the antiderivative. But again, we're going from 0 to t of a constant. So the antiderivative, and if we did apply the fundamental theorem, we would just get the square root of 2 times t. So in other words, in this case, or in this step, sorry, we're going to have s equal to the square root of 2 times t. Okay, step number 3. Step number 3 is that we're going to find t of s. So in other words, a fancy way of saying that is that we're just taking this green equation that we just found in the previous step, and we're going to solve that for t. So we have s equal to the square root of 2 times t, and we're just going to solve that for t by getting s divided by the square root of 2. All right, so that's really our first 3 steps. Our fourth step is just to rewrite this. So in step number 4, we're going to rewrite the vector function to be in terms of arc length. And really all this is taking the original, and actually, you know what, I'll write down the original so that it's on the same screen here. So we have r of t equal to cosine t, sine t, and then t. And all we're doing is taking t equal to s divided by square root of 2, and we're going to substitute that in for all the t's in this equation. So r of t of s is equal to cosine of s over root 2, sine of s over root 2, and then the last component would just be s over root 2. And that is the vector function defined now by arc length. So again, we start at t is 0. Let's say that I know we want to travel 4 units along the arc. All I would need to do then is plug in 4, 4, and 4, and what I would get in return is the position vector that would lead me to the point that I'm at. Now in the previous examples, we did the opposite. We know we started at a value, and then we know where we ended as a t value, and we figured out the arc that was covered, or the length that was covered along that arc. So we're doing the opposite. We know the length, and we're trying to figure out where the t value is. Okay, let's go to the next page and try one more. Now with this example, you can sort of see what's about to come here. This is an entire page for one problem. So this is going to be a little bit intense algebraically, but I'm going to show you a couple techniques that do help us and that we will use as we work through some of these problems. So this particular function r of t is kind of ugly, e to the 2t cosine of 2t and so on. And we want to change this. We want to change the parameter so that this function, instead of being in terms of t, is now in terms of arc length. They do give us the starting t value, which is going to be 0, kind of similar to what we had before. We'll see that there's actually a different result to this, however. So let's go ahead and organize. We have our first step is that we want to find the magnitude of r prime in terms of t so far. So we have kind of an ugly first derivative here, bunch of product rule. At least the middle term is 0. That's helpful. So we have 2e to the 2t cosine of 2t. I'm going to do a minus. I'm going to try to save some space here because remember this time we're going to take e to the 2t, but then the derivative of cosine of 2t is minus 2 sine of 2t. So I'm trying to save a little bit of room here by doing the product rule. So I'm doing the product rule of the very first component. And I just kind of grouped things together a little bit so it was less ugly. The second component is derivative of 0, thank goodness. And then we have the next one, which is really similar to what we had in the first one. We have 2e to the 2t and sine of 2t, and then plus 2e to the 2t, and then cosine of 2t. All right, that is our derivative of r. So much more complex than the last problem we have done. Now remember, our goal is to find the magnitude of this. Here's one technique or one trick, however you want to say it, that helps you with magnitude. I'm going to actually factor out the greatest common factor of each term that I have, and that's 2e to the 2t. This is a technique that will help us in the future. So we have cosine of 2t minus sine of 2t, and then 0, of course. And then we have sine of 2t plus cosine of 2t. Now it still is ugly, but at least the vector portion, not the thing that I factored out here, but this vector portion is a little bit simpler to look at. Remember, we're doing the magnitude. The reason that I factor this out is because if I take the magnitude of this greatest factor, so if I square that value and then take the square root, I'm left with it. So in other words, this is not impacted by the magnitude that I'm taking, because if I square it and then take the square root, I'm left with it. So it saves me a little bit of time. In other words, the magnitude so far is 2e to the 2t, because again, it's irrelevant to analyze the magnitude of that. Now, however, I need to do the magnitude of the rest of it. So we're going to take, and I'm going to put this into two steps here, just so that you can see the process. So we're taking this first component, squaring it. Obviously, the middle one is 0. The second component, and we are squaring that as well. You're going to get better and better at looking through these, canceling what you need to cancel. But for the time being, I am going to write this out sort of the long way. So we have 2e to the 2t. I'm going to expand this initially. So I have cosine squared of 2t minus, now I'm not going to do the whole process, but remember, if you're going to expand this this component here, we're going to get, on one side, we're going to get negative cosine of 2t times sine of 2t, and the other side, we're going to get negative sine of 2t times cosine of 2t. So in other words, what we get is 2 of those. Again, if I lost you there, what we're doing is we're just distributing, we're foiling this out. Then we have positive sine squared, of 2t. So our first set right here, I've just expanded out. Then our next one would be sort of in a similar way. We would have sine squared of 2t. Then we would have plus 2 sine of 2t cosine of 2t plus cosine squared of 2t. Now you're going to get better and better at expanding those, but for right now, just remember that when we're taking something like this first component, it's really cosine of 2t minus sine of 2t times the quantity cosine of 2t times minus sine of 2t, and we're foiling that all out to get this large set of values here, and then the same thing for that second set. Now keep in mind that we have a cancellation here, which again, we're going to get better and better at doing that quickly rather than having to write the whole thing out. So here's what we have. We have 2e to the 2t, then we have the square root of, now remember we have cosine squared of 2t and then another one over here. So I have two of those, 2 cosine squared of 2t. I also have 2 of the sine squared of 2t. So I'm going to factor out that 2. So we have 2 times this quantity. I know this is really ugly. It's okay. It will get better over time. All right. Now I know there's a 2t, but cosine squared plus sine squared, whether it's a 2t or a t, as long as it's the same, that's going to equal 1. So finally, we have the magnitude of r prime of t, might as well put a prime in there, there we go, is equal to 2 times the square root of 2 times e to the 2t. So there is our first step, a little more painful than last time. Okay, next step is calculate s. So we want to find s of t. And remember, s of t is equal to the integral. And remember, t started at 0, and then we're going to go to t of 2 root 2 e to the 2. I'm going to make it u. Remember, we're going to use that different variable there. And this is where your antiderivatives, with u subs come into play. This is technically a u sub. I mentioned in that review that we did prior to section 10.2 that I'd like you to get to the point where you could do this antiderivative without a u sub. And that is more to just think through the intuition behind it. But if you need to do a u sub, I suppose you kind of have to do a different variable because u is already in there. So you have to maybe do a v sub or something. But you're going to get an antiderivative of the square root of 2 e to the 2u. Now, how do we know that's correct? Well, the derivative of this is here. So we know that's the antiderivative because, simply put, the derivative is there. Okay, we are going to evaluate that from 0 to t, which gives us the square root of 2 e to the 2t minus, and if we plug in 0 for u, we get just the square root of 2 because e to the 0 is 1. So in other words, we have s equal to the square root of 2 e to the 2t minus the square root of 2. All right, that is step 2. We're making progress. All right, step 3. We are going to find t of s. So we're going to take the equation we just found and we're going to solve for t. So I'll write it out again. So this is going to be a little bit uglier. Let's go ahead and add the square root of 2. And then we can divide by the square root of 2. I suppose we could have done that all in one step. That would have been fine. That's all right. Now we want to convert to logarithmic form. So we have the natural log of s plus the square root of 2 over 2. I know that we could certainly simplify that down a little bit more, but that's okay. And then I'll just write this here. So we have t equal to 1/2 the natural log of s plus square root 2 over square root 2. And again, you could simplify that in a variety of ways. Let's just leave it for now. Okay, we are finally on to our last step here. So our final step is to rewrite the vector function r of t of s. So change that r of t equation, which was e to the 2t cosine of 2t 2, and then e to the 2t, and then sine of 2t. All right, so again, all we're doing here is we're taking each of the t values and we're going to substitute in this sort of ugly formula that we found in the third step there. Now notice that when we do substitute this in, we are multiplying it by 2 every time, which means the 1/2 cancels. So r of t of s would look something like this. So it'd be e to the power of natural log of s plus square root 2 over 2 cosine of the natural log of s plus square root 2 over square root 2, and then we have the same type of behavior here for this other one. Okay, we could simplify this just slightly. I know that you're wanting to be done with this right now, but remember e to the natural log is this inverse relationship, and so for this first part you actually get s plus square root 2 over 2, and you can't do much with this other one. I'll pause and write out the rest. All right, so there it is. That is our new vector function in terms of arc length, which again, I know that's really ugly, but that's the concept and it can be a fairly lengthy problem at times. Okay, that does it for this video. The next video will be on curvature. Thank you.